Tony, how you doing?
Well, how are you?
Good. Omar, what's up?
Hi.
Hey, Cody. Hey, Nate.
Hi.
Okay.
Proving that we're not.
Yeah, there are people here.
Hey, at least you can hear us.
All right, welcome everybody. Today we're going to be talking about our second series, I guess, in nuclear molecules, molecular, I don't know. That was the joke. I'm just trying to think I should start this one.
I was gonna say, you want to restart?
Hey, you probably want to retry, man.
Mulligan.
Be serious.
Be serious.
You guys are all
Good
like,
joke.
oh man, this is gonna suck. Okay.
And when you introduced it, that was a joke.
That was good.
That's
This
a
is way
good-
better than the last
Yeah, no, that's a really good joke to
Just
start
like
out.
break the ice, you know.
Yeah, just keep running with that. I like it. Yeah.
All right, welcome everybody. Today we're going to be talking about how nuclear power plants work. So, how many of you have ever wondered how a nuclear power plant does work?
Definitely.
All of you. Okay. Well, another question, have you ever wondered if they're safe? If you should be worried about maybe living close to one, or if they're safe to have at all? Well, we're going to try to answer those questions and also help you to understand how a nuclear power plant generates electricity, also to understand the process of nuclear fission, and understand the risks associated with nuclear power. So upon completion of this presentation, and we'll come back at the end of the presentation and we'll see if we were able to do this, but you guys should be able to explain the basic structures of a nuclear power plant. You should be able to explain the characteristics of uranium. You should also be able to explain the process of nuclear fission, explain the process of generating power in a nuclear power plant, and also understand the risks that are associated with nuclear power. So this is just kind of a quick look at what a nuclear power plant looks like. You've probably, some of these things look familiar to you. Yep, the cooling tower is something that most people recognize. And we're going to come back to this image and talk about each of these structures. But to begin with, we're going to start with the fuel that's used in a nuclear power plant, and that is uranium. And this is a picture of uranium ore, just looks like any other rock. It's an element on the periodic table of elements. It's right here. And the symbol is U. It's found naturally on the Earth. It has an atomic number of 92. It's found in 3 major naturally occurring isotopes. And it's as common as tin. So, is everyone familiar with what an isotope is? No? Okay. An isotope is basically, the definition of an element comes from the number of protons. That's what this atomic number is. So, uranium has 92 protons. That's its atomic number. And that is always the same. By definition, it has to have the same number of protons. But the number of neutrons in an atom can actually change. And so that's an isotope of an atom. So even though it has a different number of neutrons, it's still uranium. But this atomic weight of the atom will be different. The atomic weight you see on a periodic table of elements is actually the average of all the different isotopes as they occur naturally on the Earth. So this is 238.0289. That's what uranium is. So the isotope that is used in a nuclear power plant is uranium-235. And this is a bit of a problem because uranium-235 only makes up 0.72% of all natural occurring uranium. which is mostly uranium-238. So in order for us to use uranium in a nuclear power plant, we have to do what's called enriching the uranium. So we need to get the uranium-235 from 0.72%, we need to get it up to closer to 3.5% in this uranium. Now, if we're going to use this uranium for a weapon and a bomb, it has to be highly enriched up to about 90% uranium-235. And that's because uranium-235 is a more unstable isotope, so it's something that's able to more easily go through a nuclear reaction. We'll talk about that a little bit more. But they estimate that the easiest to mine uranium will last us for about another 85 years. This is the stuff that's not too expensive to get to, doesn't take too much effort to get to, and it's about 6 million tons. This picture here is a picture of a billet of highly enriched uranium. It's about 9.5 pounds of uranium. And just so you can understand how much power is in this uranium, 1 pound of uranium will produce as much electricity in a nuclear power plant as would 2,000 tons of coal. So it's got a lot of energy in that element. So now we're going to talk about the fission process. Has anybody heard that word before, fission? Does anyone know what it means? They can give us a quick definition. That's okay, because we're going to talk about it anyway. But fission is basically the splitting of atoms. So with uranium-235, what happens in this nuclear reaction is that we send a neutron at this uranium atom. And when it hits the uranium atom, the atom splits apart. And when that happens, energy is released in the form of heat. And also more neutrons will fly off of these atoms. And so these neutrons can now hit other uranium atoms, which can then split and produce energy in the form of heat. And this reaction can continue uncontrolled until all of that uranium has been depleted. And that's basically what we call a chain reaction. And we have ways to control that reaction, which we'll talk about. You can see here it says control rods, and we'll talk about this a little bit more too. But before we go on, I just wanted to clarify the difference between fission and fusion. So, as we already talked about, fission is the splitting of two atoms, and fusion is the fusing of two or more small atoms into one large atom. So the differences here, fission requires a low amount of energy. We just need to hit it with those neutrons and have it split, where fusion requires a lot of energy. It needs a lot of heat and a lot of pressure, because in order to get these atoms to fuse together, they have to overcome the electron force, the electrons that surround an atom. So they have to overcome that electron force so that the force of the nuclei can actually take over, and then they combine. So that's really hard to do. It takes a lot of energy. The energy produced in a fission reaction is 1,000,000 times greater than a chemical reaction. And with a fusion reaction, it's 3 to 4 times greater than a fission reaction. And byproducts from fission are highly radioactive, where byproducts from fusion are not that radioactive. Fusion is used in the atomic or atom bomb. These were the bombs that were dropped on Hiroshima and Nagasaki, or fission bombs. Today's hydrogen bombs use a fusion process. They actually combine both. They use a fission explosion to trigger the fusion reaction. And those bombs are 100 times more powerful than a fission. So now we're going to get into how all of this will generate electricity. We're going to start in the reactor. We're going to go to steam generation. Then we're going to go to the turbine and generator. And then we're going to talk about the cooling system. So back to this image here. We're going to start here with this green reactor vessel. This is where the fuel is contained. And what they do is they put the uranium-235 they form it into small pellets about the size of your pinky, and they drop it down into rods, and these are called fuel rods. You've probably heard that term before. And they'll get several of these rods together and put them into a bundle that'll has spaces in between. But they bind it together in a bundle. It's about this big, so not too big. And that is where the fuel is contained. And then we have these control rods. So what happens is this reaction begins. This reactor vessel is actually full of pressurized water. So this reaction starts, and it starts to get really hot. And this reaction will go uncontrolled unless something is in place to slow it down. And the uranium, because it's only 3.5, 235, it won't explode like a nuclear bomb would, but it can actually get so hot that the uranium will melt. And that's what a meltdown is. You've probably heard that term before, is when that reaction is uncontrolled and it melts. So that's a bad thing. So these control rods actually absorb neutrons from this reaction. If we went back to this picture here, this picture of these control rods showing that these neutrons are being absorbed so that they can't go and trigger more splitting of atoms. So the faster they want the reaction to occur, the more they pull out these control rods. If they want it to slow down, they'll put them in between those fuel rods. So as this heats up, it heats up this pressurized water and becomes superheated. But it can't boil because it's under pressure. And they run that superheated water over to these water tanks that are called steam generators. And this super hot water, they run through pipes into this water, will cause this water to boil and to produce steam. And so a high amount of pressure and steam will then rush over to the turbine and spin the turbine and create electricity in our generator. And so that's how the electricity is made in a nuclear power plant. So then we have to recycle this water because they don't want to just use water and throw it back into the environment. So it's very self-contained. So this steam is run through a condenser, which is basically pipes that are filled with cold water that this steam condenses onto. And so then that's captured and run back over to these steam generators. Now the condensing system has its own water system, and it brings in cold water from this cooling tower or from some other natural source. And then it's brought through this condenser, and as that happens, this water heats up because of being in contact with that steam. And then they run it back to this cooling tower to be cooled. And so that cycle just continues also. So any questions about any of those parts on the nuclear power plant?
So what happens if it doesn't get cooled? The cooling part goes out.
Yeah, that's a good question, because it's really important to keep this reactor temperature under control. Because if this water gets too hot, then you could have a crack in these fuel rods, and the uranium would then come in contact with water, and this could create gas and explosions. So it's really important that this temperature is kept in check. Good question, Cody.